Chapter 7, Section 1 is about multiplying monomials. So this whole chapter is dealing with polynomials, which are made up of monomials. So before we get too far into this chapter and start talking about all the things that we can do with polynomials, we need to go over what makes them up. And so we need to start first by talking about monomials and what they are, what they look like. Now, we've actually talked about monomials before. It's been a while since we talked about them, but we did discuss these briefly back in Chapter 2 when we were going over what makes something look like a monomial versus not a monomial. When we're talking about monomials, you have that word mono in it, M-O-N-O, and that means one. So we're talking about something that's like singular by itself. So a monomial could be a number, a variable, or a product of a number and variables. Product, remember, means multiplication. So I'm just going to write some examples up here for you to maybe add for yourself of things that would be considered monomials. Like I said, a monomial could be just a number, so it could just be like 4. It could be just a variable, like x. Or it could be the product, so multiplying a number and a variable. So 4 times x. Or you could have 3 times a, b. That would also be a monomial. They could even get really complicated and start having exponents with those letters, like 10x squared, y to the third, z, something like that. Another thing that you might see is something that's written with like x divided by a number, like x over 3. That is considered a monomial. Just maybe make yourself a note that x over 3, this is the same as 1/3 times x. So I can think about pulling that x like off to the side and putting that number 1/3 in front. We saw some of that happen in Chapter 6 because we spent some time in that chapter graphing. And so when we were graphing lines, we saw slope written as a fraction. And so you can really see that the fraction is sitting next to the x in that mx plus b form. So that's kind of what's happening in examples that look like that. The really big thing that we have to make sure when we're dealing with monomials is that we don't break a couple of rules. And those rules are that you can't have addition signs, you can't have subtraction signs, and you can't be dividing by a variable. Okay? So here's some examples of things that are not monomials. So I'm just going to say not monomials here and give you some examples. Not monomials would be like x plus 3. That's actually considered a polynomial, okay? Or the true word for this one would be a binomial because there's 2 terms, and bi means 2. When I look at that, it's made up of monomials. Like x is a monomial, 3 is a monomial. But because they put a plus sign in the middle, it's no longer considered a monomial because there's more than one term. Same thing happens if they were to put a subtraction sign. So if we had like 2x minus y, that would also not be considered a monomial anymore because of that subtraction sign. Again, that last rule that I underlined says divided by a variable. So kind of coming back up here, when I see that x over 3, if they had actually flipped that, so it was 3 divided by x, that's not a monomial because the variable is in the denominator of the fraction. That is different than what I had written up above. I can't pull that apart as like 3 times x because that's not what's happening. It's 3 divided by x. So that's the issue with that one. If you ever see a variable in the denominator, you cannot call it a monomial. I would say that those cases here, like this one and this one, okay, these are not the same. These are the ones that probably confuse or trick students the most. Sometimes students see a fraction and they automatically think, nope, it can't be a monomial. But remember, you have to really look at that fraction. The only time it's an issue is if there is a letter in the bottom of the fraction. So I want you guys to take a minute here and look at this example. There's 4 problems here. And what I want you to do on these lines is write either yes or no for the first question. So are they monomials? Write yes or no. And then write why. So be able to give an explanation why you think they are or are not a monomial. So I'm going to give you a minute or so to do that. Pause the video here. Give yourself a minute or so, a minute and a half, maybe 2, to do those 4, and then keep watching so you can see what it should have been. So for this first one, 3x plus 2, hopefully you said no, because it has that addition sign here. So my reason would be that it has addition. And if you remember what I said earlier, this is actually called a binomial because it has 2 terms. It's not a monomial anymore. The next one, 3xy, I would have said yes to this one. And the reason why is they're just multiplying your number and variables. It's the product of a number and variables. There's no plus signs, there's no minus signs, there's no division by a variable. It's not breaking any of those 3 rules that we had up above. For this next one, we have 2x all over z. Hopefully you guys saw that z down there in the denominator, and that made you want to put no, because we are dividing by a variable. Hopefully this last one didn't trick you, because we talked about that up there. It's 4x divided by 3. You should have said yes for this one. Something that you could have done to give an explanation is that you're taking 4/3 times x, or you could just think of that as 4/3 x, like that. So you're just you're able to pull that variable off to the side, and you just have that fraction 4/3 sitting next to it there. All right, now that we kind of know what makes something a monomial, what makes something not a monomial, we're going to start getting into the different operations that we can do with monomials. And in this section, we're focusing on multiplying. We have a couple of properties that we need to go over. This first property is called the product of powers. This means that if you're multiplying terms, like monomials together, there is an easy way for us to be able to figure out what the answer would be. If I have something like in these examples, b to the 3rd times b to the 5th, what they're saying that we can do is look at those exponents 3 and 5, and we can actually just add them together to get 8. Now, if you're not really sure, like, how did they get that, or where did this come from, this rule, if you think about what b to the 3rd means, b to the 3rd means that you're taking b times itself 3 times. So you're taking b times b times b. This is b to the 3rd. Now I'm multiplying that times b to the 5th. So using kind of the same reasoning, that means that there should be 5 b's. So this is b to the 5th power. Now what I'm doing is I'm multiplying these together, and if I count all the b's that I have up here, there's 1, 2, 3, 4, 5, 6, 7, 8 of them. So this comes out to be b to the 8th power. And the shortcut there is to take those exponents and add them together to get that 8. So that's the shortcut that we can use. But what that really means is that you're taking those monomials and you're spreading them apart by expanding them. And then you can think about counting them all up. But this shortcut is useful because imagine if I had something like x to the 210th power times x to the 340th power. You know, if I was trying to expand that out, that would take me forever to do because there's so many x's. So instead, what I can do is add 210 plus 340 and that would be 550. And that's a lot faster than me having to write out 210 x's and then write out 340 of them and then trying to add them all up. So the shortcut is very helpful when you're dealing with problems like that, that are huge. Now, chances of us seeing things like that aren't super likely, but it's a nice rule to know that we have so that we can do these types of problems a little bit quicker. So I give you an example down here that really, again, just kind of goes over exactly what I did up there. So I've got x squared times x to the 4th power. X squared, remember, is 2 x's. X to the 4th is 4 x's here. And so if I multiply them all together, or if I add up all the x's that I wrote out there, that's really 6 of them. So it's x to the 6th power. And the shortcut, again, is just to add those exponents to get to that final answer. So why don't you guys take a minute here and do these two practice problems. All right, for this first one, I would have taken 3 plus 7 to get y to the 10th power. For this next one, anytime you see a letter by itself, it technically has an exponent of 1. We just don't see it written there. So you should have taken 5 plus 1 to get b to the 6th power. Now, we're going to take what we were just doing and we're going to expand it a little bit. We're going to start adding some more things to our problems here. We're still multiplying these terms together. But now what they're going to do is start having numbers, like coefficients in the problem, and possibly more than one letter. And when you're doing these types of problems, it's really helpful if you can kind of break it into smaller, more manageable pieces. The first thing that you want to do is match your like bases together. So look for the things that look like each other. What are your coefficients? So remember, coefficients would be those numbers that sit in the front of the problem. What letters are you dealing with? Do you see common letters? Do you see that they both have A's or they both have B's? When you do those kinds of things and being able to match with the bases, then you can start multiplying the pieces together. So after you have them matched, step 2 would then be to multiply your coefficients, those numbers that sit out front, and then take care of the exponents with the letters, just like we were doing before. So let me show you kind of my thought process when I'm looking at this example that I've got worked out here for us. So I've got these two monomials that both have numbers and variables attached to them, and I'm trying to multiply these together. The first thing I do is I try to match up my bases. So I see that like my 6 and my 2 are my coefficients, so I grouped them together. Then I looked at what else I had. So I had x to the 3rd and x to the 5th, and so I matched those up together. Then I also saw that I had y's, y squared and y to the 4th, and so I matched those up together. So hopefully you can kind of see how I went from here to here by kind of matching up my bases. Okay, so that's like step 1. Now, as you guys get more and more skilled at doing these types of problems, I don't necessarily need to see you write that out every single time. Some of you are going to just be able to start multiplying things quickly and just write down what they're going to be. But if this step really helps you so that you can figure out what needs to go with what, then I would encourage you to do this step. Now what I'm going to do is multiply my coefficients. So I did 6 times 2 and I got 12. So I took care of step 2. And then for step 3, we're going to add the exponents of like bases. So my exponents on the x's are a 3 and a 5. So 3 plus 5 got me 8. So that's how I got x to the 8th power. And then for the y, I have 2 plus 4 for those exponents, and that got me 6. And that's how I got y to the 6th power. So hopefully that kind of shows you how we're grouping things together, and then how you can kind of see if I start combining them, how you're going to get those final answers. Let's look at another example here together before you have a chance to practice. So this next one here, we have 3 and 5. So I'm going to group those together because those are my coefficients. Then I'm going to look at my like bases. So I have x to the third and x over here. So I'm grouping those together. Now my first term has y to the fourth. The second one, though, doesn't have any y's at all. So I'm not going to be able to pull anything down from that second one. That doesn't really matter. I'm not going to change my y to the fourth then. It's just going to stay exactly how it looks right now. Now I'm going to go ahead and multiply. So 3 times 5 would be 15. This x to the third times x, remember that x has a 1 for an exponent. So 3 plus 1 would be 4. So x to the fourth, and then y to the fourth needs to come down, and it stays unchanged. Now, both of these examples, so this one that we just did up here had, x's and y's and numbers, and so did this one, had x's and y's and a number. Now, sometimes I have students say, well, how do I know, like, if I have different letters, and maybe they're, like, really random. Maybe it's not like ABC. Maybe it's like D and then M and then Q. And they're asking, like, well, how do I know what order to put the letters in? I would always try to make sure that you're putting your variables in alphabetical order. So if you're dealing with problems that have lots of letters involved and you're writing your final answer, we're going to want them to be in alphabetical order, and you're going to want your number, your coefficient, to be out front. So maybe you need to write yourself that note too. Put coefficients out front. Because there are going to be some problems that you see where they kind of mix up what letters they're giving you in the first term versus the second term. Like sometimes you'll see that the first term on like a problem like this one doesn't have an X, but the second term does. And that can be a little bit confusing then because students maybe forget that that other X was there, and so they don't think about it until the end. So just make sure that you're trying to put your letters in alphabetical order. Same with like coefficients. If the first one doesn't have a number other than 1 written, but the second term does, or maybe the third one down the line does, you're going to want to make sure that you put those coefficients in the front. Just because it's proper form, it's called standard form when we're putting them in order like that. It's just going to make some things that we're going to see as we go further along in this chapter easier to kind of keep track of, especially when we start getting into combining like terms. You're going to want to have a very specific process in how you write your terms so that you can easily match your terms up together. So those are just a couple of extra notes I wanted to add in there in case you ever do run into that case. Now on this page, in your guys' packets here, there are 3 practice problems. There's this first one, the second one back with X, Y's, and Z's, and then this last one, okay? I want you to pause your video right here, and I want you to take a few minutes, 5 to 7 minutes maybe, to try to do these 3 problems. Make sure you're trying to write them in order, alphabetical order, and put those coefficients out front. When you think you've got your problems done, or if you want to maybe do them like one at a time and then check this first one and then pause the video again and check the next one, that's fine too. But I want you to try to do these on your own and then come back and watch however that works for you so that you can see what the answer should have been. All right, for this first one, my numbers that I match up are 2 and 5. My letters, I had a squared and an A. Then I had a B and a B to the 5th, and then C to the 3rd and C squared. If it helped you to kind of group them together in parentheses like I'm doing right here, that's great. If you don't need that step, that's fine too, if you're starting to feel more comfortable with these types of problems. So I had 10, a to the third, b to the sixth, because remember that has a 1, and c to the fifth. For this next one, there's only a coefficient in the second term, not the first one. So we're going to want to make sure that for our final answer that we did put 8 out front. Now looking at my letters, I have x to the third and x to the fourth here. I only have a y in the first term, and my z is happening in both of them. So got a little bit of a mixture here. This is kind of starting to change it up a little bit on you and make sure that you're kind of paying attention. So we should have put 8 first, because coefficients always go first. And then our letters. Now, alphabetically, x comes first in the alphabet. So we've got x to the third, x to the fourth. So that should have been x to the 7th power. And then your y comes next, so y to the third. And then your z, z to the 4th. For our last practice problem here, highlighting our like terms one last time, 10 and 3 go together. There's no x in the first term, but there is in the second one, x to the 5th. Then I've got y to the 7th and a y, z squared and z squared. 10 times 3 is 30. Now, alphabetical order, I do want to make sure I bring that x to the 5th down first, even though there's no x over here in this first term. I'm just going to drop that down. And for your y's, we've got y to the 8th power, and then z to the 4th power. All right, this next property we're going to talk about is called the power of a power. A little bit different than what we saw earlier. Earlier we were talking about product of powers, which means that you're multiplying things that have exponents. Now what we're doing on these problems is that you have a term that already has an exponent, and it's going to be raised to another exponent. So that's why they call it a power of a power rule. We do have a shortcut for this one as well. This one looks a little bit different than what we saw before. You can see how you've got like b to the 3rd here, and all of that is being raised to the 5th power. Now the shortcut for these, because those exponents are like only separated by that parenthesis, they are kind of butted up next to each other there. The shortcut says that you can take those exponents, 3 and the 5 for this example, and you can multiply them together. What this means, again, if you think about how I expanded the one example on the previous page, if I were to expand this one, this means that I have b to the 3rd 5 times, because b to the 3rd is being raised to the 5th power. So that would look like this: b to the 3rd times b to the 3rd times b to the 3rd times another b to the 3rd, and finally one more time. There's 5 of them. Now remember though, b to the 3rd means that you're doing b times b times b. And I'm doing that for 5 of these times. So you can see how on this one, when I expand it out, there's 15 of these b's here. This is b to the 15th power. So that's why instead of adding like we were doing before, we do need to multiply our exponents, because it is written a little bit differently, and the context of the problem is a little bit different too. So another example over here that I see is I've got g to the 6th power, and that's being raised to the 7th power. So I need to take 6 times 7, which would be 42. Now, again, if I were to expand that one out, it would take me more time, because I would have g to the 6th 7 times, and then all those g's would have 6 of them. So I would be spending a lot of time writing those out if I were expanding them, which is again why these shortcuts are really handy when we're trying to do these problems a little bit quicker. Now let's take a look at an example where we've got maybe numbers and multiple letters happening here. So in this one I've got 3 x squared y to the third. Now all of that is in parentheses and we've got a 4 as our exponent here. What you can really think about doing is that you're taking that 4 out here and you're applying it to all the terms on the inside. So it goes to the 3, it goes to the x, and it goes to the y. So you can see how I have that written as 3 to the 4th power for the number. Then for my x, I have x, and then x was squared, and now I'm taking it times that 4 from the outside. And for my y was cubed originally, and then I'm taking it to the 4th power. Then I just have to do the math. So 3 to the 4th power, if you don't know that, I would use a calculator, grab one out, punch this in. So 3 to the 4th power comes out to be 81. For your x, you're going to take 2 times the 4 this time, and you get 8. And for the y, you get 3 times 4, which would be 12. And that's your final answer. These ones should look differently than what we just were dealing with. We're not taking 2 separate monomials and multiplying them. We're taking a singular monomial now. It's all in parentheses, or it's all in some type of brackets, and it's being raised to a new exponent. Okay, so make sure that you can distinguish the difference between what we were just doing and what these problems look like right now. There's a couple of practice problems here for you. There's this first one, and then there's this next one down here. I want you to go ahead, again, pause the video here, take a few minutes to try to do these couple of practice problems on your own. So for this first one, if you need to think about rewriting it so that you can really see how that 2 on the outside is going to affect all these terms, because you're distributing here. So I'm going to write this out separately. So it's 2 squared. We're doing that. Then we're taking x. It's already to the 5th power, and so you're going to take 5 times 2. And then for your y, which is already to the 3rd power, you're taking that times 2 as well. So 2 squared would be 4. X goes to the 10th power now. 5 times 2 is 10. And y should have been y to the 6th power. Similar thing happens on this practice problem. You would have 4 now to the 4th power. X was to the 3rd, and you're taking that times 4. And the y, remember, has a 1 technically, and you're taking that times 4. 4 to the 4th power should be 256. X should now be raised to the 12th power, and y should be to the 4th power. Now, there's going to be times where they give us a really complicated problem, or at least it might look like it's really complicated, but we can use these properties that we've been talking about to help us simplify these bigger, more complicated looking problems. If you have fractions and like numbers and then you're raised to multiple powers, so we have like all these parentheses, all these brackets, all these grouping symbols, what we can do is kind of break this into smaller pieces here where we can do the inside parentheses first and then distribute the top or distribute the exponent to both parts of the fraction, the top and to the bottom. And then we'll distribute the second shortcut or the second exponent. Now I am going to show you a shortcut to this type of problem too, just in case it works well for some of you, then you can use it going forward with other problems as well. So this first one I got worked out pretty much all the way here, so you can kind of see the sequence of steps. What they did for this first one is they worked with the inside portion first. So they took this 3 and they distributed that to the 2/3 and to the x squared. Now that 3, when I go to the fraction, I have to do it to the top and the bottom of the fraction. So notice how they wrote 2 to the 3rd and 3 to the 3rd. because anytime you raise a fraction to a power, it's going to do it to both the top and the bottom. Then what we did is we dealt with our x. So x was already squared, and then it's being raised to the third, so you had to multiply that. Now we simplify. So 2 to the third became an 8, 3 to the third became a 27. So now we've got a little bit of a bigger fraction here. And then x to the 6th power now, because 2 times 3 is 6. Now we're going to do it again. We're going to take this 4, and we're going to distribute to the fraction and to the x. Again, when I distribute the 4 to the fraction, I had to do it to the top. So I have 8 to the 4th, and I have 27 to the 4th. Then when I do my x, it's 6 for that original exponent times 4. Then I just expand these out. So 8 to the 4th is that 4,096. Getting really big numbers here. 27 to the 4th is even bigger. It's that 531,441. And then I have x to the 24th power. So for some of these, you might start to get really large numbers, really large fractions, just because of the nature of the numbers that you're maybe raising to these exponents. Now, here's a shortcut that I've had some students discover, and it really seems to work well for some. So I am going to just kind of explain that, and if this works well for you, you are welcome to use it on your own. The thing that students do on the shortcut is they look at what they had originally over here with those exponents on the outside. So they had that 3 and that 4. And what they decided to do is multiply them, because they're using that product of, or the power of powers property here. So they're taking 3 times 4, and so they rewrote this as 2/3 x squared, because that's what's inside, and then now it's raised to the 12th power, because they took 3 times 4. Okay? Now, this looks just like the problem that we were just dealing with. The only difference is that, yes, I did throw a fraction in here at you. But that 12 now is going to get used for the fraction and for that x. So we have 2 to the 12th power, 3 to the 12th power, and then for your x, you're taking the 2 exponent times 12. And when you do this, 2 to the 12th power still comes out to be 4,096. 3 to the 12th power comes out to still be that 531,441. And then x is raised to the 24th. So we get the same answer that we got over here, just using a little bit fewer steps. So if you like that shortcut, you can understand how they got it started. All they had to do to get it started was just multiply those outside exponents, and then they just kind of distributed them through. They only had to do it one time though, and then they got their final answer. So I'm going to give you guys a chance to try this on this practice problem. You can either do it the original way I showed you up above, or you can use the shortcut, whatever you prefer. So go ahead, pause the video here, take a minute, watch this, and then come back to see how it all works out. So I am going to show both ways, the original way and the shortcut way, just to make sure that I hit both of them in case you chose one of the two options here. So the first thing I did is I took this 2 and I distribute. So I had 1 squared over 2 squared, and then x with a 3 is now being multiplied to a 2. And so that comes out to be 1/4 x to the 6th power, and all of that is still being squared. So now I had to do that one more time. So 1 squared over 4 squared, and then x to the 6 times 2, and my final answer comes out to be 1/16 x to the 12th power. Now, if you used your shortcut method, the first thing you did was you multiplied the 2 times 2 here, and so you rewrote this as 1/2 x to the 3rd, and all of that's raised to the 4th power. Then we took this 4 and we distribute that into the problem. So we have 1 to the 4th over 2 to the 4th, and then your x now is 3 times 4, and we still got 1/16 x to the 12th power.